Hello viewers, welcome to Ada. In this question we are asked, what is a bipolar junction transistor? And we have to draw the C mode and CV mode in order to describe the relationship between alpha and the beta, which are the current amplification factor in C mode and CV mode. Okay, so let us start with what is a bipolar junction transistor. So bipolar junction transistor is made of three semiconductor regions. Okay, semiconductor are mainly of either N-type semiconductor or P-type semiconductor. Okay, and the bipolar junction transistor is made of three semiconductor regions. Okay, it can be either NPN or PNP, where this is the N layer. Then after we will be sandwiching a P layer within another N layer. Okay, so this is a NPN where first semiconductor is N type, second is P type, then third is N type. Similarly, we can sandwich a N type semiconductor between two P type semiconductors. So this is a PNP semiconductor. Now each of these three semiconductor regions have a name. For the NPN type semiconductor, the first N-type region, which is this region, this is known as emitter. Okay, so this region is known as emitter, and this P region is known as base. Okay, so this is known as base, and this N region is known as collector. Okay, so this terminus remains the same for both the NPN type transistor and the PNP type transistor. But the thing is, in the NPN transistor, the base is P type and the emitter and collector are N type. But in the PNP, the base will be N type and the emitter and collector will be of P type. Okay. So this is the basic fundamental concept of bipolar junction transistor. Okay. Now, bipolar junction transistor, these are the particularly the three terminals, and there are specifically two junction. Okay, one junction is the AB junction. This AB junction means the emitter base junction. In a NPN semiconductor, as I have said, first layer is N, second layer is P, third layer is N. Okay, so this N layer is the emitter, this P layer is the base. So between the emitter and the base, a junction will be formed, right? Which is the PN junction concept. This is the PN junction concept. So between the N and the P layer, a junction will be formed, which will have a voltage of EB, or we can say EB-PN junction. Okay, this will be EB-PN junction, and similarly between P and N, as I have said, this is the base, this is the emitter, and this is the collector. So between the base and collector, another PN junction will form, which will be named as CB. Okay. Now transistor operates in three mode, or we can say four mode, but the fourth mode is not of so much importance to us. So the four modes are cutoff, actives, reverse actives, and saturation. Okay, so these are the four modes, and we will write the configuration of EB junction and CB junction. So during cutoff mode, EB junction is reverse biased and CB junction is also reverse biased. So the PN junction CB is reverse biased and the PN junction at the EB will also be reverse biased. In actives, the EB junction is forward biased and the CB junction is reverse biased. And in the reverse actives, the EB junction is reverse biased and the CB junction is forward biased. And in saturation, both the junctions will be forward biased. Okay. So this is the basic concept of the bipolar junction transistor. Next, we will draw the CE mode and CV mode of configuration, because from this two mode of configuration, we will get to learn about the concept of current amplification factor in both of the CV mode and CE mode, which is denoted by, in our case, alpha and beta. Okay. So let us at first start with CE mode, right? So let us start with CE mode. So the CE mode is just the basic concept behind CE mode is the emitter region. The emitter region is grounded, okay? Or the emitter terminal of the bipolar junction transistor is connected to a ground. Like how? So this is the symbol of a bipolar junction transistor. This straight line denotes the base, and this terminal, which is this arrow represent the flow of current. This terminal is the emitter terminal, and this upper terminal is the collector terminal. So as I have said, the emitter terminal would be grounded. Okay. So this emitter terminal will be connected to a ground, and we will be applying our input voltage, or we will apply the voltage to the base. Okay, we will apply the voltage to the base. So this is our input signal or input voltage signal, which is represented by Vi. Okay, so this is a DC regulated voltage supply. So this is our input voltage to the base, and after that we will be receiving, this is RC, collector resistance, and across this RC we will be receiving our output voltage. Okay, so this RC we can also consider this is connected to ground. The one end of the resistance, collector resistance, is connected to ground, and the voltage across this collector resistance will be V output, which is denoted by V naught. Okay, so let us learn about the current amplification factor in this. So in this CE mode, as I have said, the emitter region is grounded. Okay, so the current which is flowing to the emitter terminal is particularly flowing to the ground. Okay, so this current will have no significance in CE mode, or IE current will not exist in our scenario. Okay, so basically we are supplying the input voltage, or we are giving the power supply to the base. So for this power supply, which is denoted by Vi, we will be getting a current of IB. Okay, so this IB is the input current, right? This IB is the input current, and this is applying to the base of the CMOS transistor. Okay, and where we are taking the output, we are taking the output across this collector terminal or the collector resistance. Okay, so the current which is flowing to the collector resistance is equal to IC. Okay, so this is our output current and this is our input current. So by amplification, it means the signal that we are applying at the input of the transistor, how much it will get amplified across the output. Okay, so this is the main concept of the current amplification factor. For example, let us assume that we have applied a signal like this. Okay, and at the output we are getting a signal like this. So as we can see that this signal is amplified because this amplitude is increased. Okay, so we have to determine the amplification factor to say by how much factor the amplitude is increased. Okay, so this is the input current IB and this is the output current IC. So in the CE mode, the current amplification factor, which is denoted by beta, is equal to IC divided by IB. Okay, so this beta is equal to IC by IB. This is the current amplification factor in the CE mode. Okay, now in the CB mode, I am representing the CB mode here. So in the CB mode, similarly as I have said in the CE mode, the emitter terminal is grounded. The full form of the CE mode is common emitter. Okay, so the emitter terminal is grounded. Similarly in the CB mode, the base terminal is grounded. Okay, so what happens in the CB mode? In the CE mode, the emitter terminal was grounded. We were applying the input voltage to the base and we were getting the output from the collector. So in this scenario, so this is the transistor. So in this scenario, the base will be grounded. Okay, the base will be grounded and we will be supplying the input voltage to the emitter terminal. Okay, and similarly, we will be receiving our output voltage across this collector resistance. Okay. So similar to the C scenario, we will be applying some signal like this, and from the collector terminal, we will be getting some signal like this. But we have to note that the amplification in common emitter mode is very much high than the amplification in the common base mode. The reason is, we will see that in the emitter terminal, the current which was flowing is IE, which is the emitter current. Here the base current IB is 0, or we can say that the base channel is not of significance to us because we are applying the input to the emitter terminal. So the input current will be IE, and at the collector terminal, the output current will be IC. So the current amplification factor is denoted by IC divided by IE. Okay. So the main reason the amplification factor in the CE mode is greater than CB mode, because in BJT, what happens? So this is the emitter terminal, this is the base terminal, this is the collector terminal. This is N type, this is P type, and this is N type. So as it is N type, it consists of lot of number of free electrons. Okay. It consists a lot of number of free electrons. So the main purpose of this emitter terminal is to provide as much current as possible to the collector terminal. Okay. So what happens when this emitter base junction, when the emitter base junction is forward bias? So when a PN junction is forward bias, the potential barrier between the two N type and P type, it gets lowered. So the holes from the base will come to the emitter, and the electrons from the emitter will go to the base. Okay. Now this emitter, this is highly doped. Okay. So this is highly doped. I am represented by 3+, but this base region, this is very much lowly doped. Okay. And this collector region is moderately doped. Okay. So if we assume total number of 100 electrons goes to the base, so the out of 100 electrons, only 5 number of electrons will recombine with the holes of the base. So as a result, the base current which is generated in our scenario, which is IV, it is the recombination current, which is very much low, which is very much low. Okay. So the value of IV is not so high. And the job of this base is to supply those electrons as much as possible to the collector terminal. Okay. So the value of IV is very low, and the value of IE and IC are almost identical. Okay. The value of IE and IC, the collector current and the emitter current, are almost identical. Okay. So if we consider the emitter current is around 7 milliampere, then the collector current will be almost about 6.8 or 6.9 milliampere. So they are almost equal. So what happens in the CE mode? The current amplification factor is equal to IC divided by IB. Okay. So this IC, as I have said, this will have a very high value, up to 6.8 milliampere. But this IV has a very low value, which is almost 0.01 or 0.02 milliampere. So if we divide this IC by this IB, the value of beta will be around, the value of beta typically ranges around from 50 up to 200. Okay. So this is the value of beta. But in this current amplification factor, which is alpha, which is the amplification factor in CB mode, the value of IC, as I have said, the value of IC and value of IE are almost identical. So they are always less than equal to 1. Okay. So here we can see the amplification factor, the value of it is very much high, but here in this case, the amplification factor value is very much low. So we will be getting more amplification in CE mode rather than the amplification in the CB mode. Okay. So now the relationship between the alpha and beta. So alpha is equal to IC by IE, and beta is equal to IC by IB. Okay. So let us do one thing. Alpha is equal to IC by IE. Okay. So we are multiplying it with IB and divided it with IB. Okay. So what happens? IC by IB, it will be equal to beta. Okay. It will be equal to beta, and it will be IB divided by IE. Okay. So now in this scenario, as I have explained, the the main supplier of the electrons is mainly this emitter. Okay. So this emitter current is responsible for the generation of the collector current as well as the base current, because the collector current is generated by the electrons which is supplied from the emitter to collector, and the base current is generated from the recombination of the electrons and the holes in the base ring. So this IE is equal to IB plus IC. Okay. So here in this case, we can represent IE is equal to IC plus IB. Okay. If we substitute this value of IE in this region, we will be getting beta into IB divided by IC plus IB. Okay. And from it, if we take IC common, we will be getting 1 plus IB divided by IC. Okay. So, yeah, if we take IC common, we will be getting 1 plus IB by IC. So, this IC by IB is equal to beta. So, IB by IC, it will be equal to 1 by beta, right? So, beta divided by beta into 1 plus 1 by beta. Okay, so this will be the value. So, I am writing in this page here. So, the expression we are getting is beta divided by beta into 1 plus 1 by beta. So, this beta will cancel out each other. So, here we will be getting this beta into 1. It will be 1 plus beta divided by beta. So, if we do the revision, we will be getting beta divided by 1 plus beta. Okay. So, this is the relation between alpha and beta, where alpha is the current amplification factor in the CB mode, is equal to beta divided by 1 plus beta, where beta is the current amplification factor in the CE mode. Okay. Thank you.